Hey, AP Chemisters, this is Mrs. Vandelay bringing you Blankwalle, Chapter 14, Section 3, Part 2. So we learned earlier what the law of mass action was. We learned the significance of what K was. If it's a really big value, then it favors the products. If it's a really small value, then it favors the reactants. So now what we're going to do in this section is look at the relationships between the equilibrium constant and the chemical equation itself. So you can do like three things to the original equation, all right? So the first modification is, what if I reverse it? So if I'm looking at my original equation, all right, what am I going to do if I want to flip it so that my reactant becomes my product, so my products becomes the reactant? So what are you going to do? You're going to invert the equilibrium constant. Okay, so what does that mean? Well, if I start off with the original equation, okay, here's my forward K, or my K1, if you will. Okay, well, what's my reverse reaction? What's the law of mass action of that? Don't you get something like this? So what's the relationship between the two? All right, well, if I look at here, at my K forward, all right, what does it mean to invert? Well, I'm going to do 1 over my reverse. And what happens when I do the 1 over this? It's like, you know, what should I do with my denominator? I'm going to flip it. So if I flip the denominator to get a 1, then I'll flip the numerator, and that's what it'll be equal to here. So what's the relationship? My K forward is equal to the inverse of the K of the reverse. Okay, so it's just the flip. It is 1 over that. Okay, let's look at the second one. All right, so if you multiply the coefficients by some factor n in this case, all right, you're going to raise the equilibrium constant to the same factor. Oh, is this important? Okay, and we're going to come back to this in section 4 or 14.4, why this is an important idea. All right, so if you multiply the coefficients in the equation by a factor, you're going to raise the equilibrium constant to that same factor. So here's equation number 1. So my K1, I'll put a little 1 here, is equal to what? Same law of mass action that we saw before, right? Products over reactants. Now, what about equation number 2? Okay, what about this K factor? Well, what is it equal to? C raised to the Cn, or the 3n, A raised to the n, B raised to the 2n. So what is the relationship between 2 and 1? Well, K2 is equal to the original raised to a certain value. Okay, and now finally, last but not least, number 3, let me scroll down here. If you add 2 or more individual chemical equations to obtain an overall equation, this is like Hess's law. You like Hess's law. Multiply the corresponding equilibrium constants by each other to obtain the overall. Okay. So if I'm looking at K1, all right, wouldn't that be 2b or b squared, I'm sorry, over a? And what about K2? Isn't that c to the third over b2? And like I said, this is Hess's law. Look what I can do here. Do you remember what I called these in chapter 13? I called them intermediates, didn't I? So I can cancel them out. So it was created here, and then it was used up. That's an intermediate. And so what's my overall equation? Isn't it that? Well, so what is my overall equation here? All right, well, I know it's going to be c cubed over a because I'm looking at this, right? But look, whoops, look what happens here. All right, well, is that equal to, look what happens, K1, right? Isn't that K1 times, oops, come here, K2, and look what happens to my B's. All right, don't they cancel out, oops, excuse me, as well? Yeah, look at these. They cancel out just like those canceled out earlier. So what is that overall relationship? Well, K1, which is this, times K2, which is this, will equal my K overall. Okay, and that's going to be very, very handy. Okay, so the next page gives us some problems where we're going to practice these. All right, so problem number 6 is the following equilibrium concentrations are observed for the Haber process at 127 degrees. All right, so here's the equation, and there's my equilibrium constants. All right, So now calculate the value of K at 127. Does it favor the forward or the reverse? So why don't you guys go ahead and write down the law of mass action and then plug in the numbers. Oh, by the way, you need a calculator, and then see what you come up with. All right, go ahead and do that right now. So you need to pause this for a little bit and actually work through the problem. All right, welcome back. So I found the KEQ. I'm going to put the right up here. All right, I'm going to have the concentration of ammonia squared divided by my reactants, nitrogen and hydrogen gas cubed. All right, and now I'm going to put in the actual value. So here's my ammonia. Here's the value of it. So it's 3.1 times 10 to the negative 2 squared, divided by my concentration of my products, okay? Excuse me, my reactants, 8.1 times 10 to the negative 1, or yeah, negative 1, and 3.1 times 10 to the negative 3, and I got to cube this as well. So I'm hoping you know how to use your calculators, and so this is what my calculator came out with, and I only have 2 sig figs, so I end up with 38,000, okay? Now, does it favor the forward or the reverse? Well, this is a pretty big number, isn't it? So if it's the big number, that means my numerator must be big, and so that means it favors my products, doesn't it? All right, so it favors the forward reaction. Okay, now look what's going to happen in letter B. So look at the difference between A and B. All right, I flipped these, didn't I? All right, so all right, calculate the equilibrium concentrations or the equilibrium constant. So I'll do the same things I did before. This time my products are nitrogen times hydrogen cubed divided by ammonia squared. All right, so next I will plug in my numbers, and let me see here. I do believe it is these numbers. All right, I lost my dividing number. And what does that equal to? I believe it equals to that. But wait. What did we say happened if we were going to reverse it? Isn't it also equal to 1 over the forward reaction? So is that equal to 1 over 38,000? Get out your calculators, and what do you get? What is 1 divided by 38,000? Well, I think you're going to get, what? This again. You get the same answer. Isn't that amazing? All right. Let's look at question letter C. All right, so it says calculate the value of the equilibrium constant at 127 for the reaction given by the equation. Does it favor the forward or the reverse? All right, so what did I do? Look at the difference between C and A. What's the only difference? Oh, you multiplied everything by half, didn't you? All right, well, let's do this. Let's go the long way. Here's KQ is equal to, what's my law of mass action? Take my product. I only have one coefficient, so don't raise it to anything. But I do have fractions down here. Remember how I told you how messy those units would be? I told you you're going to get some fractions. That's kind of yucky. And so what is that equal to? Well, 3.1 times 10 to the negative 2. And then I have this here. Go ahead and literally use your calculator and make sure you get my answer, right? Plug this in, come back when you're done. Okay, did you get 194? All right. Now, was there an easier way you could have done this? Of course, Mrs. Vanderwille. All right, what did we say earlier? That if you have a different coefficient, just raise that equilibrium constant to whatever you multiplied everything by. All right, I'll do that. So my K1 was 38,000 raised to a half. Isn't that equal to the square root? Isn't a half power the same as a square root power? Yes, it is. And I get this time 190. Well, folks, it's the same thing, isn't it? Because I only need 2 sig figs. This is 190 with 2 sig figs. This is 190 with 2 sig figs. They have the same answer. All right, so let's finish answering the question here. Does it favor the forward or the reverse reaction? Well, K is greater than 1, so it favors the forward reaction. Oh, you know what? Did I ask you that? Oh, I never went back and answered this one. Does it favor the forward or the reverse reaction? Well, what kind of number is this? This is a pretty small number. It's like 0.0000026, isn't it? That's really small. So it favors the reverse reaction, all right? You're going to have a lot more products, or excuse me, a lot more reactants than your products, okay? Sorry, I didn't write that down. All right, so the reaction for A yields 2B has an equilibrium constant of K equals 0.010. Hey, before we go ahead and do anything, is this A is in equilibrium of 2B, is it going to favor my products or my reactants? You think about it, what do you get? I definitely said your reactants, and I hope that's right. And so look at letter A. Again, it's the reverse. So what do you notice about that? If it's the reverse, what are you going to do? Well, what's the relationship between that and the initial? Great, so if it's the reverse, then isn't it 1 over that number? So what would that make it? Well, equals 1 over, what was your initial K value, 0.010? Hey, don't use your calculator. Can you figure this out without a calculator? What's 1 divided by 0.01? Well, what's 1 divided by 1? 1. What's 1 divided by 0.1? 10. What's 1 divided by 0.01? Did you get 100? Yeah, maybe you should try that without a calculator. What about the next one? So I take my initial reaction, and what do? I multiply everything by a half, right? So what would that mean? Isn't K2 equal to a half of K1? Well, what is, if you raise something to a half, what is that equal to? It's the square root. So what's the square root of 0.01? Hey, don't use your calculator. Figure it out in your head. What's the square root of 0.01? What's the square root of 1/100th? Did you get 1/10? Hopefully you did. All right, let's see what the next one is. Look at this one. You both inversed it and multiplied by a half. You flip-flopped it and you changed the coefficients, all right? So it's the reverse and it's a half of the original one, okay? So what do you think you're going to do here? Well, I think we're going to do this. Take 1 over and then kf to the half, right? Right? And then what? So what's this equal to? 1 over, well, what was the square root of kf? Oh, it's right up here, isn't it? 0.1. So, hey, mental math, what's 1 divided by 0.1? 10. You're right. Let's see what problem number 8 says. All right, consider the following reaction and the equilibrium constant, 25. So here's the reaction, and here's your K. So calculate this for the following reaction at the same temperature. Well, how are these two different? Well, you flip-flop these, didn't you? So here's my reactant, now it's my product. Here's my product, now it's my reactants. What else changed? The coefficients. So you both reversed it and you doubled it. So how is this going to work? Why don't you pause this and see what you get? All right, this is what I got. K2 is equal to 1 over K of the initial of forward, I guess you'd call it, squared. Why? Because it's doubled. Up above, we've been taking things to the halves. Why? Because we multiply everything by a half. Here, we multiply it by 2. So you're going to square it. So it's 1 over 2.2 times 10 to the 6th squared. You can get 2.1 times 10 to the negative 13th. Hey, does it favor the forward or the reverse reaction? The reverse. So up here, all right, look at this. If you're going to go this direction, this is a huge number, isn't it? All right, it's like 2.2 million. So you're going to have a whole bunch of products and very low reactants. So if I flip the reaction around, you're still going to favor the same species. They're just in a different spot. They're now the reactants, not the products, okay? So this is the end of section 13.3. I'm sorry, 14.3. So don't wait to be great. I hope this helped. See you later. Bye-bye.